Hey everyone, I want to make a quick video. I don't have that much prepared, but I want to go over the Mississippi problem because even though you might think you understand this problem, it's showing up in more complicated problems and you don't know what to do. So I'm going to go over it again, and I want to make sure that you can see it inside other problems. So I call it the Mississippi problem, and that's how many ways can you order the letters in Mississippi. Okay? So the Mississippi problem is you have 11 letters here, right? So you have 11 letters, but you have duplicates. You have 4 I's, you have 4 S's, and you have 2 P's. So if you treated them as individual, you would overcount because you cannot tell the difference between an I, right? An I is just an I, an S is just an S. So you can't tell the difference between them. They're not unique. So if they're not unique, then you'd overcount by treating them as being separate letters. However, to find how many ways you can do something like this, you have to kind of treat it like that at first. So if we want to understand how many ways we can order this, well, we know order matters, but it's not a permutation. So what do? What we do is we think first, if they were unique letters, if there were 11 different letters, how many ways could you order those? You have 11 spots and 11 unique letters. So how many ways can you do that? That's 11 factorial. Most people don't have a hard time seeing that that would be true if you're taking finite, of course. But we overcounted. How much did we overcount? Well, we overcounted the 4 I's here, and we overcounted them being unique. So we overcounted by 4 factorial for them. Okay? We also overcounted for the S's. Okay? We overcounted 4 factorial for the S's. Okay? Then we overcounted for the 2 P's because you can't tell the difference between P's. So it's that. And it's approximately 34,000. I can't remember how much it is. I think it's 34,720 or something like that. What really matters is that you can get to this. Okay? Calculation, that's not as big a deal. I'm sure everyone can multiply and all of that. You can cross it out. But what's really important is that you see why we're dividing. It's because we would overcount by treating them as unique letters. Now, even if you're a student and you think you understand that problem, which I hope you do, it can show up in unsuspecting ways. So there's other problems where they're asking you for the probability of a different scenario, and the only method you can do is to do this method. And that's where I'm seeing people fall short, is that they understand it with words, but they can't find it in other types of problems. So let's look at a different problem, and I want to show you how it's the same. Okay? So, let's say you have a set of, let's say you're making some word, okay? And it is 7 letters. Okay? It's 7 letters long, but you can only choose between X and Y. Okay? You only get to choose between these two letters. Alright? So it's 7 letters long, but you only get the choices of X and Y. What if you're asked the probability of finding if X was for the first 2 slots? Was the first 2 letters. Okay. Now I want to draw this out just in case you're not following what kind of question we're looking at. So 1, 2, 3, 4, 5, 6, 7. We have 7 letters here. I can put any combination of X and Y here for the sample space. But the problem wants to know if X has to be for the first 2. So if X has to be here, then what's the probability of this occurring? Well, if X has to be here, then you must be implying that Y is over here. Okay? That's only one choice. Okay? I didn't get a choice between how this worked. So there's only one way that works, by the way it's set up. But what's the total sample space? Now I see that I forgot something. In these questions, they would say you only have 2 X's and 5 Y's. And I forgot to put that. Whoops. Okay. So if you only had 2 X's and 5 Y's, and you're making this, what would be your total sample space? So this is the number of ways the event can occur, but what's the sample space? The confusion with the sample space is that if you have 2 X's and 2 Y's, I don't know, is it 7 factorial? I can't tell. How can I'd have to figure out, well, I could put an X in the first slot and in the last slot, and the rest could be Y. Or I could do that. Or I could put it as we just did, the first 2 are here, and then you got the rest Y. Or X could be sorted through all these Y's. And how many different ways is that? And the problem is, it's really hard to figure out without overcounting. So this is actually the same as the Mississippi problem, because there's no uniqueness between the X's. Okay? An X is an X. So what you can actually do is you can say, well, if they were all different, it would just be 7 factorial. Okay? That's if they were all different. But we know we must have overcounted. Okay? How much do we overcount? Well, we have 5 Y's, and we can't tell the difference between 2 Y's. So I must have overcounted by 5 factorial with them. Okay? And I overcounted by 2 factorial for the X's. Alright? So this is how much I overcounted, and this is if I just treated them all unique. Okay? So what's that? That's 7 times 6 over 2 times 1, 3, 21. Okay? So the probability of this event occurring so the probability of the event turns out to be 1/21. Okay? And I apologize I didn't set this up before. It slipped my mind because I didn't rehearse this before. So, this is showing up in your homework. This is showing up, and they're having a hard time counting once we get to the sample space. Most students aren't having any trouble counting the actual event, because it turns out it's just 1. But the sample space is confusing because you have 2 x's and 5 y's. And with all this, it gets confusing of where you should put an x and where you should put a y and how you would count that. How you would count this. Okay? So this is an example of where the Mississippi problem can show up in other probability problems. And it really is the best way to resolve that issue. It showed up in our sample space in this problem. There could be other problems where it'll show up in your event or something like this. But it can be a portion of your problem and not the entire thing. In a previous video, I showed the different ways you can do dad. You can spell the word dad. And you can actually just count them. So how many ways can you spell the word dad? Like this, you could have D-D-A, or you could have A-D-D, right? That's just 3 ways. Right? Just 3 ways. Because we can't tell the difference between 2 different D's. But, so the systematic way of doing this, if you have a larger, like Mississippi or in the problem we just did, you can treat them as if they were all different, all unique letters. That's 3 factorial. And then how much did you overcount? That's 2 factorial. Okay? So that's 3 times 2 factorial over 2 factorial. And that reduces to 3. And that's what we know is true. We already knew this one was just 3. But this one's easy enough where you can actually just count them. You don't have to do this. But I'm just trying to show you that this system works for very large systems. That's a poor choice of words, but I hope that helps. I mean, make sure that it does. Make sure that it does make sense. Because when you have things that are in order, and it matters if they're in order, this kind of stuff can really show up. And really, it's the only method I can think of that you can solve that problem. Combinations won't do it for you because order matters. And if you just simply use a permutation, you run the risk of overcounting or undercounting in some cases. Let's think of another problem. I'm really doing this on the fly here. Maybe I'll replace this video later on with a more well thought out one. Sometimes I see where you have problems where you have to think about people are in chairs but in a row. Okay? So let's say you have 7 chairs. I should spell the word chairs right. You have 7 chairs, but this includes Tommy. Okay? You have 7 chairs, and this and I should say 7 people as well. 7 chairs don't include Tommy. That was silly. So you have 7 people, including Tommy, and you have 7 chairs. Okay? Now, what if you're asked for the probability of Tommy being able to sit first or in the first chair? So if we're looking for the probability of Tommy is first, well, instinctually you know if you're looking for the probability of Tommy being first, order must matter. If order matters, we know we can't do combinations. Okay? So it must be some kind of permutation or multiplication principle. Alright. Well, how do you figure that out? So the probability is the number of ways the event can occur over the number of the sample space. Okay? So, how many ways can Tommy sit first? Alright, you have 7 chairs, and you have 7 people. What's the probability he sits in the first chair? Now, I had a student that clearly, he kind of thought about it differently, and he could clearly see that the answer was just simply 1/7. Because he thought of, if it was just Tommy, that what would be the chance that he would randomly sit in the first seat? And normally you would think of how many different ways can everyone sit in the chairs with Tommy being first. So let me draw a picture. 1, 2, 3, 4, 5, 6, 7. So Tommy's first, so I only had one choice there. I only get one choice. But then I have 6 other people. 6, 5, 4, 3, 2, 1. So that's how many ways Tommy could be in the first seat. Okay? Well, what's the sample? This is the number of ways the event can occur. What's the number of ways that it could have with no restrictions? Well, that would be 7 factorial, right? 1, 2, 3, 4, 5, 6, 7. You have 7 times 6 times 5 times 4 times 3 times 2 times 1. This is a permutation. This is a permutation. This is the number in the sample space. And what we have here is, this is just 6 permutation, 1, 2, 3, 4, 5. And this is 7 permutation, 7. Okay? So this, you can use permutations. And that's fine. So you just take these numbers, you take the product of these numbers, and you divide it over these numbers. And lo and behold, you'll get 1/7. No surprise, right? So these types of problems, you order mattered. You can use permutation. But there's some particular problems where order matters, and you really have to worry about overcounting because things are not unique. People are unique. You can tell the difference between Tommy and Sarah. You know these people. But you cannot tell the difference between a couple different ones or a couple A's, or you can't tell the difference. In science, you can't tell the difference between electrons and protons. And so it comes up in science as well. It's not just abstract math that this stuff comes up. This comes up in real life science research every day. So, yeah, I mean, the Mississippi problem is a big deal. It's a real good way of not overcounting when when things are not unique, but you're using them more than once. This video is basically just a ramble. I hope that somehow helped. We did a permutation problem. We did a few of the Mississippi problems. So watch out for that. If you're noticing that you have a bunch of different spots, order matters, but you have things that aren't unique, think about that Mississippi problem. That could be the resolution of your problem, okay? So I hope this helps. Comment, tell me how terrible I did, and I'll see you then, okay?